Welcome everyone to AI Ascendancy, the podcast where we bridge the gap between cutting-edge AI research and real-world business strategy. Today, we're diving into something truly fascinating, the idea that large language models might be learning to think about their thinking much earlier than we previously believed.
Thanks for having me. It's a topic with pretty significant implications for how we build and deploy these powerful tools. The standard view has been shifting.
Absolutely. We often associate complex abilities like reflection, the model examining its own reasoning, with later stages like reinforcement learning or fine-tuning. Think of it like teaching a kid basic grammar versus teaching them to critique their own essays.
Right, the refinement stage. But this new research suggests that essay critiquing skill might start developing way back in kindergarten, metaphorically speaking.
Precisely, the paper we're looking at, Rethinking Reflection in Pre-Training, challenges that timeline. It argues that the seeds of reflection are sown during the massive pre-training phase itself, where models just learn from vast amounts of text data.
And they developed a clever way to test this. It's one thing to say it happens, another to measure it, especially during pre-training. Measuring emergent abilities is notoriously tricky.
So how did they tackle that measurement challenge? You can't just ask a half-trained model, "Are you reflecting yet?"
If only. No, they created what they call adversarial datasets. The core idea is to take standard reasoning problems, math word problems, coding tasks, logical puzzles, and deliberately introduce errors into the chain of thought reasoning provided to the model.
It's like giving someone directions with one wrong turn included. Can they still reach the destination by spotting the mistake and correcting course? That's the essence of the test.
They distinguish between two types. Situational reflection is when the model examines reasoning chains from another source, maybe a different model or, in their case, algorithmically generated errors. Self-reflection is the harder task, reflecting on its own previously generated incorrect reasoning.
From a business perspective, this distinction is crucial. Situational reflection is like quality control. Can the model evaluate external information or outputs from other systems? Self-reflection is more like internal process improvement. Can the model identify and fix its own flaws? Both are valuable, but self-reflection hints at more autonomous capabilities.
And how do they actually trigger this reflection in the tests?
This is one of the most intriguing parts. They often simply append a trigger phrase like "wait" to the end of the faulty reasoning chain. It's almost absurdly simple, but it acts as a prompt for the model to pause and reevaluate.
It does sound almost like AI mindfulness. Wait, take a computational breath. Did that calculation actually make sense? I wish debugging my code was that easy.
Chuckles, so just adding weight can make a difference.
The results suggest yes, significantly. The paper shows models often can reflect even without the trigger, but adding weight markedly increases the rate of explicit reflection, where the model actually verbalizes spotting the error, like saying, "Wait, that step seems wrong because," and improves accuracy.
They even tested this against extremes, no trigger versus a very explicit trigger like, "Wait, I made a mistake." The simple "wait" prompt seems to hit a sweet spot, nudging the model towards explicit correction without giving the game away entirely. It's like a gentle nudge versus a loud alarm bell.
Let's talk about the findings across pre-training. Did this ability just suddenly appear, or did it grow gradually?
It's a gradual emergence. They tracked performance using checkpoints from the ALMO 2 model family at various stages of pre-training, from billions to trillions of tokens processed. The data, like their Figure 1, clearly shows a steady improvement in solving these adversarial reflection tasks as pre-training compute increases.
The correlation is quite strong. A Pearson correlation around 0.76 on average between accuracy on these tasks and the logarithm of pre-training compute. More training time directly translates to better reflection capabilities, even before any specialized fine-tuning.
This really changes the calculus for model development. We often think of pre-training as building the raw engine and fine-tuning as adding the steering and brakes. This suggests pre-training is already installing a rudimentary navigation system that gets progressively better. It means the quality and duration of pre-training might be even more critical than we thought for downstream reasoning abilities.
So it's not just about knowing facts, but developing the machinery to reason about those facts, even potentially flawed ones.
Exactly, and they measured how the models correct themselves. Implicit reflection is when the model gets the right answer despite the bad prompt, but without explicitly calling out the error. Explicit reflection is when it does call out the error.
And what's fascinating is that as pre-training progresses, not only does overall accuracy improve, but the rate of explicit reflection also increases. The models become more likely to show their work in correcting the mistakes.
Building on Expert three's point, the accuracy achieved via explicit reflection also strongly correlates with pre-training compute. So, models don't just get better overall, they specifically get better at explicitly identifying and fixing errors as they train longer.
Are there specific domains where this is more pronounced? They tested math, coding, logic, knowledge.
Reflection seems ubiquitous across domains. They saw it in math problems, GSM 8K, GSM 8K Platinum, coding challenges, Crux Eval, logical reasoning, BBH, and even knowledge tasks, Trivia QA. Of course, the nature of reflection might differ. In math, it's often catching a calculation error. In coding, it might be spotting a logical flaw in the proposed code.
Think about real-world applications. An AI assistant reviewing legal documents needs to spot inconsistencies, situational reflection. A system optimizing a supply chain might need to identify flaws in its own proposed plan, self-reflection. Seeing this emerge early is promising for building more reliable AI.
You mentioned self-reflection is harder. How much harder, and does it also improve with training?
Significantly harder, yes. The models are tested on problems they already got wrong, so it's inherently a challenge set. But even here, they saw improvement. While the absolute accuracy is lower than for situational reflection, the ability to self-correct, and particularly the rate of explicit self-reflection, increases with pre-training compute.
Figure 5 in the paper shows this for a coding task. Accuracy on self-reflection problems is low initially, but climbs steadily. Interestingly, the rate at which models explicitly state they made an error seems to increase even faster. They learn to recognize their mistakes before they consistently learn to correct them.
Here's a slightly contrarian thought, though. Everyone's excited about explicit reflection because it's measurable and looks like human reasoning. But what if the real powerhouse is implicit reflection, honed through trillions of tokens? Maybe the most robust models are the ones that just absorb the correction mechanism so deeply they don't need to talk about it. We might be focusing on the tip of the iceberg because it's visible.
Ooh, interesting point. Expert 6. So, the quiet competence developed during pre-training might be underestimated.
Potentially, explicit reflection is great for debugging and interpretability, no doubt. But for sheer performance on complex tasks, maybe that deep, almost intuitive correction learned from massive data exposure is the more scalable path, even if it doesn't give us neat aha moments in the output. It's harder to prove, harder to measure, but could be powerful.
That's a strategic point too. If implicit reflection scales better with pre-training, it reinforces the value of investing heavily in that initial phase. It becomes less about complex post-training recipes and more about building the strongest possible foundation. Measure twice, cut once, or perhaps pre-train massively, fine-tune judiciously.
I see Expert 6's point, but the paper does show that for recovering from these specific adversarial examples, explicit reflection becomes increasingly dominant with more pre-training. For the GSM 8K Platinum task, Figure 3 shows most of the accuracy gains come from explicit reflection. So at least for overcoming known errors, being explicit seems key.
And the explicit classifier they built, while having decent precision, had lower recall. This means they might actually be underreporting explicit reflection, so the trend they found could be even stronger in reality.
Let's shift gears slightly to compute. The paper touches on the trade-off between train time and test time compute. Can you unpack that?
This is a hot topic. Think of train time compute as the investment made building the model, parameters, tokens. Test time compute is the cost of running the model to get an answer, which can involve complex prompting, generating multiple attempts, etc. The question is, can more investment upfront, train time, reduce the effort needed later, test time?
The findings suggest yes, specifically for reflection. As models get better pre-trained, more train time compute, they need fewer nudges or less complex reasoning chains at test time to solve the same reflection tasks. Figure 6 illustrates this. For a fixed accuracy level on the adversarial GSM 8K Platinum, models trained longer need less test time compute, fewer generated words tokens using the weight trigger mechanism.
This is a classic CapEx versus OpEx discussion for compute resources. Do you spend more capital expenditure upfront on a massive pre-training run to potentially lower your operational expenditure inference costs later? This data suggests that for tasks requiring robustness and reasoning, the upfront investment pays dividends in efficiency down the line. It's like building a factory with better, more automated machinery, higher initial cost, lower running cost per unit produced.
Does this hold true beyond the specific models they tested? They focused on ALMO 2, but also looked at QN2-5.
Yes, they show results for the QN2-5 family in Figure 7. While the specific numbers differ, the general trend holds. Larger models, more parameters, implying more pre-training compute generally, perform better on these adversarial reflection tasks across the board. This suggests the phenomenon isn't just an artifact of one particular model architecture or training run, but a more fundamental property of scaling pre-training.
So, if we were advising a company choosing a foundation model, what does this research imply?
It suggests looking beyond just benchmark scores. Understanding how a model was trained, particularly the scale of its pre-training, might give clues about its inherent robustness and reasoning capabilities. A model with massive pre-training might be better equipped to handle unexpected inputs or reason through complex multi-step problems, even if its baseline benchmark scores are similar to a less trained model.
It also highlights the potential value of checkpoints. Accessing intermediate checkpoints, as the researchers did with ALMO 2, allows you to see how these capabilities develop. For large-scale users or developers, this insight could be valuable for selecting the right stage of a model for a specific task. Maybe you don't always need the absolute final checkpoint.
And it encourages us to develop better evaluation methods. Simple accuracy isn't enough. We need methods, like these adversarial datasets, that probe deeper reasoning skills and robustness. As Peter Drucker supposedly said, what gets measured gets managed. If we only measure surface-level capabilities, we might not incentivize the development of truly reflective models.
Let's think about future implications. Where does this research point?
One clear direction is understanding what in the pre-training data fosters reflection. Is it exposure to specific reasoning patterns, dialogues, debates, error corrections? If we can identify the key data ingredients, we might be able to enhance reflection more efficiently during pre-training.
Another is refining the measurement. Can we create even more nuanced adversarial datasets? Can we improve the classifiers for explicit reflection, perhaps moving beyond simple trigger phrases? And how does this pre-training reflection interact with later fine-tuning, or RL? Does a strong foundation make post-training more effective?
There's also the question of mechanism. How exactly does the model implement reflection internally? Is it specific circuits or attention patterns? Understanding the underlying mechanics could lead to more targeted ways to improve it.
And building on my earlier point, how do we better measure and leverage implicit reflection? If a model consistently avoids pitfalls without explaining why, that's still incredibly valuable. Maybe we need tasks that reward robust outcomes regardless of explicit justification.
For businesses, the key takeaway is that the foundation matters immensely. Investing in models with extensive, high-quality pre-training might be crucial for deploying AI in complex, high-stakes environments where the ability to self-correct or evaluate information critically is paramount. It's moving beyond just pattern matching to something resembling rudimentary reasoning and quality control.
This has been an incredibly insightful discussion. We've gone from the surprising discovery of reflection emerging early in pre-training to how it's measured using adversarial challenges, the role of simple triggers like weight, the trade-offs in compute, and the significant implications for both AI development and business strategy. It seems the journey to more robust and reliable AI might start much earlier than we thought. Any final thoughts?
Just that this underscores the complexity hiding within these models. We're still peeling back the layers. It's like deep-sea exploration. We keep finding unexpected life forms in the depths of pre-training.
Agreed, and it emphasizes the importance of open research, like making model checkpoints available, which enabled this study in the first place. Transparency helps us all understand these systems better.
For leaders, the message is stay curious. The assumptions we hold about how AI works are constantly being updated. Keeping abreast of these fundamental shifts is key to making smart strategic bets on AI.
Excellent points. Thank you all, Expert 1, Expert 2, Expert 3, Expert 4, Expert 5, and Expert 6, for shedding light on this fascinating area of AI research. That's all the time we have for today on AI Ascendancy. Join us next time as we continue to explore the frontiers of artificial intelligence. This paper challenges the idea that reflection develops only after pre-training. The research shows reflection abilities begin during language model pre-training. Reflection involves examining reasoning and adjusting based on evaluation. The study distinguishes situational reflection on external information. It also examines self-reflection on the model's own reasoning. Explicit reflection involves outputting text acknowledging errors. Implicit reflection involves correcting errors without stating so. Researchers created 6 datasets with flawed reasoning to test reflection. These flawed reasoning chains are called chains of thought. The datasets cover mathematics, coding, logical reasoning, and knowledge. Models were tested on their ability to spot and fix these errors. A simple trigger phrase like "wait" helped prompt models to reflect. Experiments used almost 2 model checkpoints from various pre-training stages. Results show reflection appears early and improves with more pre-training compute. Accuracy on reflection tasks strongly correlated with increased compute. Models increasingly used explicit reflection as pre-training progressed. This explicit reflection significantly boosted accuracy on error-filled tasks. Self-reflection on the model's own mistakes proved harder but also improved. Models became better at explicitly noting their own errors over time. Similar improvements were observed in QN 2.5 models. More pre-training reduced the test time effort needed for similar accuracy. A limitation is that detecting explicit reflection might undercount instances. These findings show pre-training is crucial for developing reflection. This work provides a framework for studying reflection during model training. Future work could explore how post-training builds on these pre-trained abilities. Identifying data that enhances pre-trained reflection is another next step.